Today, I would like to talk about the data encryption standard, and sometimes called the DES. Now, DES was issued by the National Bureau of Standards. Now it's called NIST, the National Institute of Standards and Technology. The DES was the first encryption algorithm the US government approved and then widely adopted by industries that needed a strong encryption. Now, DES use um, the, the plain text of 64-bit block and also 56-bit key, and which was regarded as a very strong encryption algorithm at the time. Now, it was replaced by the more secure advanced encryption standard in 2001. Okay, so the DES is a block cipher, which means that the plain text will be divided into blocks of the same size. Okay, so here's the plain text. Okay, now the plain text will be divided into blocks of the same size. Okay, now the DES use a Festo cipher structure. A Festo cipher structure which divides each data block into two halves. Now, these two halves are processed through multiple runs. Now, in DES, each block consists of 64 bits. Each block consists of 64 bits. And then each block will be encrypted with 56-bit key, which generates also a 64-bit output of the ciphertext. Okay. Now let's take a look at the diagram here. So on the top of the left-hand side is the 64-bit plain text. Okay, 64-bit plain text. The 64-bit plain text passes through the initial permutation, a process called initial permutation, that rearranges the bits to produce the permuted import. Which is also 64-bit. Now, then, this is followed by a phase consisting of 16 rounds. Okay, a phase consisting of 16 rounds of the same function. Okay, round 1, round 2, round 16, they use the same function. Now, each function involves both permutation and the substitution function. Okay, so it involves the permutation and substitution. We'll talk about this in the next slide. Now, the output of the last round consists of 64 bits that are function of the import plain text and the key. So the output is the function of the import, initial import, and also the key. Okay. And then after this, the left and the right are swapped to produce the pre-output. So that's called a 32-bit swap. So we're gonna create a pre-output. Now finally, the pre-output is passed through a permutation that is the inverse of the initial permutation function. Okay, which is the inverse of the initial permutation function. And then we're going to produce the 64-bit ciphertext. That's the whole DES process. Okay. Now this is actually the left side, which basically process the plain text. Now the right hand side, is the key. Okay. So on the right hand side of the diagram, the 64-bit key is reduced to 56-bit through the process called permuted choice 1. So initially, we also import the key as a 64-bit. Okay. So the 64-bit key will pass through the permuted choice 1, which is a process that reduced the 64-bit to 56-bit. Now that's the reason why, because the permuted choice 1 is one-time process. Okay, so that's the reason why most of the time we call the key of the DES is 56-bit key, not 64. Even though we initially import the key as 64, but it will immediately reduce the size from 64 to 56 by removing 8 bits. Okay. Now the reason why we want to put the 64-bit key is because we want to make it consistent with the plain text. Because plain text use 64, so on the key side, we also put the 64-bit key, but the 64-bit will immediately reduce to 56. Okay. Now, then for each of the 16 rounds, okay, for each of the 16 rounds, okay, on the plain text side, a subkey is produced. There's a key 1, key 2, and all the way to key 16. So for each round, a subkey is produced. Now, to produce a subkey, basically we use the combination of the left circular shift and also a permutation called a permuted choice 2. Okay, so the 56-bit key will pass through a process called a left circular shift. Now, so which will actually eventually create a subkey. Okay, 48-bit subkey, and the 48-bit subkey will mix the the plain text side to produce a 64-bit output in each round. So that's pretty much the whole DES process. Okay. Okay, so now let's take a look at a single round of the DES algorithm. Remember, for the DES, there are 16 rounds. Now, so let's take a look at the, each of the round. Now, on the right side is the single round of the DES algorithm. Okay, so the input for a round is divided into 2 parts. Okay, now let's assume this is round 1. Okay, let's assume this is round 1. So the input is basically the 64-bit, after the initial permutation. So then it's divided into 2 halves. The left half is called L0. The right side is called R0. Okay, so that's the L0. That's R0. And then, for round 2 and round 3, the input is going to be, L1, R1, L2, R2. So, depend on which round we're talking about. So suppose this is round 1. So the import is going to be, 64-bit. Okay. So which is divided into 2 half, L0 and R0. Now, after the round 1, the output will also be 64 bits. The left one we call L1, the right side we call R1. So in general, we use L I minus 1, R I minus 1, and the output will be L I and RI. Okay. So the L1 is pretty straightforward. If you look at this path, the R0 will eventually passed as L1. So for the next, as an output, the L1 is actually the R0. Now the difficult part is the right side, the R1. To create the R1, we're going to go through a couple of functions. Okay, so the first, the R0 will pass through a process called expansion permutation, and we call E-table. Okay, now E-table is actually a kind of a matrix, so which is listed in the table C.1 C. Okay, we'll talk about this later. So this is called expansion permutation. So R0 is 32 bits. Okay, now after the expansion permutation, the 32 bits will be expanded to 48 bits. So we actually added additional 16 bits, okay, to create 48 bits. Now these 48 bits will then be mixed with the 48-bit subkey. In this case, it's the K1 because this is round 1. So the subkey is also the K1. The K1 is also 48. Remember, we mentioned this here. Okay. Now, this is 48 and this is 48 key. Okay. So two 48 bits string were passed through the operation called exclusive OR. Now, what is exclusive OR? Exclusive OR is an operation on the binary numbers. It's pretty simple. We'll talk about this later, but for exclusive OR, it's almost like some kind of arithmetic operation. So, well, if you have a bit like a 0 and another bit 0, if the operation, the exclusive OR operation, so here we can use either XOR or we can simply use a plus and with a circle outside. So the exclusive OR operation, 0 plus 0, that is not a plus, exclusive OR operation. So 0 exclusive OR 0 is 0. 0 exclusive OR 1 is 1. 1 exclusive OR 0 is 1. And 1 exclusive OR 1 is 0. So from here, it looks like the exclusive OR is almost like a addition, but it's not, because 1 plus 1 is 2, but a 1 exclusive OR with 1 is also 0. So that's the operation we're going to use for the exclusive OR operation. Okay. Now, after you mix the 48 bits after the expansion permutation with the subkey, which is also 48 bits, we generate another 48, which basically mixed the information on the plain text with the information on the key side. So that one generates 48 bits. Now that 48 bits gonna pass through another operation called substitution slash choice. Now it's also called S box. The S box basically reduced the 48 bits to 32 bits. Now it's back to 32 bits. Okay, so first we expand it from 32 to 48, and then mixed, with the sub key to create the 48, and then you shrink to 32. Okay, and then we're going to pass through an operation called permutation, which is also a table that we reshuffle the binary bits. Okay, now after the permutation, a new 32-bit string is created, and then the 32 bits then mixed with L0, okay, another exclusive OR operation, but this time it's a 32 bits, versus 32 bits. Okay, so then we're going to generate R1. Okay, so in this case, the right side, after all these process, now we actually, these process put together with the dashed line, we call this F function. Okay, it's called the F function. Okay, so the right side R0, after pass through the F function, and then the output is 32 bits. Okay, and then exclusive OR with the left side L0, and this is going to generate R1. So L1 and R1, which is the output of the round 1. So now after the round 1, then we got a 64-bit with L1 and R1. Okay. Now round 2 is pretty much identical as with round 1. Okay, it's identical to the round 1, but the input of round 2 is L1 and R1, and the output of the round 2 going to be L2 and R2. So we can continue that way. So we're going to go through 16 rounds. Okay, so eventually we could generate this 64-bit output after 16 rounds. So also on the key side, okay, so after the permitted choice 1, we have 56 bits. Okay, now this 56 bits is also divided into 2 halves. Now initially, it is called C0 and a D0, because the left side is also the round 1. Okay, so this is also corresponding to round 1. Now then we're going to pass through the left shift for both C0 and D0, which is also, so that's 28 bits, and then after left it's also 28 bits. So that combined 28 plus 28 is 56 bits, and then we pass through the operation called permitted choice 2. Okay, it's also basically called a permutation and a contraction. So it's permitted choice 2. The permitted choice 2 reduce the 46-bit to 56-bit to 48-bit. Okay, so 56-bit, which is 28 plus 28. So reduced to 48. That's the sub key. Okay, the sub key then mixed with the plain text side. Okay, so that's the whole process. That's the process inside round 1 and the round 2 and the round 3. They are basically identical. Now, let's work on an example. Now, this is an example of single round of DES. Now, even though DES has 16 rounds, but all the rounds are identical. So that's the reason why we just need to take a look at the example of single round. Now, the plain text is a 64-bit, binary string organized into 8 by 8 matrix. Now, similarly, the key is also 64 bits organized into 8 by 8 matrix. Now, there's an index for each of the bit in the plain text. Okay, it doesn't matter how you organize the plain text, whether it's going to be organized into 8 by 8 or just flattened into 64-bit string. So the first bit has an index 1. Okay, the index basically represents the location of this particular bit. So the second bit has an index 2. Okay, and then we have index 3, and the last one in the first row has an index 8. So now we have a next one, the index 9. The last one in the second row is the index 16, index 17, 24, 25, 32, 33, 40, 41, 48, 49, and 56, 57, and 64. 64 is the index of the last bit in the plain text because the plain text is 64. And similarly, we can put the index 1 here and index 8 here, and then the last one is 64. That's the index for the key, the bit in the key. So we pick a very special plain text. So you can see that the first row contains all 0. If you think about these, convert this into a decimal, which represents 0. The second row represents the decimal 1, 1 0, the decimal 2, 1 1 represent decimal 3. So it's a 4, 5, 6, and a 7. Similarly, the key is also very special. The first row contains all 0. The second row contains all 1, all 0, all 1, all 0, all 1, all 0, and all 1. Okay. Okay, here's the overview of this example. Now, this is the import plain text. Okay, we mentioned this in the previous slide, right? So that's a plain text, which is a 64-bit. And that's the 64-bit key. Okay, so the first step is the initial permutation. Okay, now we'll talk about how we actually use the initial permutation because it's defined in the table C.1a. Okay, so after the initial permutation, you're going to create a 64-bit output. Now, that 64-bit output becomes the input of the first round. Okay. Okay. Now, first half of the 64-bit, which is 32-bit, is called L1, L0, and the second half, 32-bit, is the R0. Okay. So that's a left side, that's a right side. Okay. And then the output after the first round are going to be L1 and R1. As was discussed in the previous slide, L1 was directly copied from R0. Okay, so L1 is the same as R0, but R1 is very complicated because you're gonna first start from R0, pass through a couple of F functions like expansion permutation, and then create the 48, expand to 48 and mix the key, the sub key K1 from the key side, and then generate a 48-bit output and pass through the ACE box and reduce back to the 32 bits, and then you perform the permutation and then do the exclusive OR with the L0 that eventually generate the R1. So R1 is very complicated. Now on the key side, so initially the key was imported as 64-bit. As we mentioned that most of the time we call BS use the key 56. The reason for this is because the 64-bit key was immediately reduced to 56-bit. Okay, after the permuted choice 1, so it just reduced to 56-bit, and the 56-bit, is also divided into two parts, C0 and D0, and then we do the left shift for both C0 and D0, and then pass through another process called a permuted choice. The 56-bit basically will shrink to 48 bits. Okay, now that's the key one. Okay, and that 48-bit gonna mix with the 48-bit on the plain side, plain text side. Okay, so that's the overall picture of this example. Okay, so let's talk about the first process in the DES, and it's called initial permutation. Okay, now take a look at the diagram. So here we have the plain text, which is 64-bit plain text. Now the plain text is going to pass through the first process called initial permutation. Now initial permutation is defined in the table C.1a. Okay, I listed C.1a here. So that's the table C.1, permutation tables for DES. A is the first table. Okay. Now when you look at the table, then the number, each number in the table represent the index in the original plain text. Okay. So for example, the first index is 58. So that means the bit in the index 58 will be moved to the first location here. Okay. Now what's the bit with the index 58? So I have 57, which is this bit 0, and the next one is 58. So this is 58. Okay, so 58 will be located here in the first row, first column. Okay, now what's the next one? 50. Let's take a look at the plain text. Where's 50? 50 is this, because the one before 50 is 49. Okay, so that's 49. So 50 is here. Okay, it's also 0. Now, if we continue to look at the next index and the next index and next index, you'll find a pattern, right? So where's 42? 42 is this, because look at the 41. It's, 41 is just right before 42. And where's 34? This is 34, okay? And the next one's 26. Next one's 18, 10, and 2. So if you look at the original plain text and look at the second column from bottom up, the second column from bottom up will be moved to the first row after the permutation, initial permutation. So these are all 0. Okay, so that's this one. Okay, so that's going to be row number 1. Now, where's row number 2? Here. The first index is 60, second index 52, 44, 36, 28. Now, where is the bit in 60 in the index 60? Okay, 60 must be in the last row, right? So 57, 58, 59, and 60. Okay, that's 60. Now what's 52? You will find out 52 is this. Okay, 44 is this. So eventually you will find out the second row after the permutation, initial permutation, will be this column. Okay, it's a column 4. Okay, so they are all 0. Now if you continue to look at this, you will find out row number 3 after the initial permutation will be the column, okay, number 6. Okay, so that's the row number 3, which is column number 6 in the plain text. Okay, so for example, if you take a look at the first index 62, so that's 62. Okay, and then 63, and the last one's 64. So we have this. Okay, so that's the row number 3. Now what about the row number 4 after the permutation? It's a 64, 56, that's the last row. Okay, so which is 1 0, 1 0, 1 0, 1 0. It's always bottom up. So we're done with the first 4 row, and then look at the next 4 row. 57. Where's 57? Okay, 57 is, let me actually change the color for the pen. I changed to green color. So where's 57? 57 is this. Okay, and 49 is this. So if you look at the 5th row after the initial permutation, it's actually the first column in the plain text. So that's row number 5. And then we will find out that's row number 6, row number 7, row number 8. Okay. So let's see. So row number 5, it's all 0. Row number 6, row number 5, row number 6, it's all 0. And row number 7, all 0. And row number 8, it's a 1100, 1100. Again, from bottom up. Okay. So that's the initial permutation. So that's the 64-bit after the initial permutation. Okay, so here's the 64 bits after the initial permutation. Okay. Now, so this is one here. That's the output after the initial permutation. It's a 64-bit output after the initial permutation. Now, these 64 bits is divided into two parts. The top part, and also we call the left part, we call it L0. Okay. And the right part, we call it R0. Okay. And then this becomes the input for the first round in the DES. Okay, so after the initial permutation, we actually convert the 64-bit plain text into a 64-bit output. So that's the initial 64-bit plain text, and then after the initial permutation, we generate an output. Okay, so and then we divide the output into two parts. The first 32-bit is called L0, and the second 32-bit is called R0. Okay, so this output becomes the input of the round 1 in the DES. Okay, now this is a diagram for a round. Okay, so all rounds are the same. Round 1, round 2, round 3, they are identical. So for round 1, we know the input is going to be L0 and R0. Okay, so let's take a look at the R0, because R0 will pass through a dotted line, which is called the function F function. Okay, F function consists of a couple of different processes. The first one is called expansion permutation. Remember, R0 is 32 bits. Okay. Now, after the expansion permutation, it becomes 48 bits. Now, how can we do that? Okay. So let's look at the expansion permutation, which is defined in table C.1c. So that's the table C.1c. Now, if you look at the table, it contains three parts. Okay. The first, the left column, and the right column. The middle part is a matrix which contains 8 rows and 4 columns. Okay. Now look at the number. This is an index. Okay. So that's the original R0. Okay. That's the original R0. Now, so in order to actually use the expansion permutation table, we have to reorganize the original R0 from 4 rows and 8 columns into 8 rows and 4 columns. This is a very simple process. So the first 4 bits becomes the first row. The second 4 bits in the first row becomes the second rows, and then that's the third row, fourth row, and the fifth row, sixth row, seventh row, and the eighth row. So we actually reorganize. We actually don't change any numbers, but we reorganize from 4 by 8 to 8 by 4. Now, even the index is not changed, okay? So the first one is index 1. The last one is index 32. So the first one is index 1. The last one is index 32. So even index is actually is the same for each bit. So now how can we expand the 32 bits to 48 bits? We're going to expand this by adding 2 columns. Let's first look at the right column, okay? The bit we're going to add contains the index defined in this table. So the first one we're going to add contains the index 5, okay? So it's kind of like a natural expansion because you have index 1, 2, 3, 4, and then we add 5. So which is the next bit, okay? So that's the index 5 has a 0, value 0. So we add this index 5. And next one is index 9. So index 9 has a value 0. And next one, index 13, it's also 0. Index 17 is also 0. Index 21 is also 0. Remember that the previous one's index 20, right? So that's index 21. And index 24, yeah, we got a 1, so it's a 1. Index 29, it's 1, so we got a 1. And the next one has an index 1, so it's actually looks like a circular way. So index 1 has the value 0. Okay, so we add an additional column. And we're going to add another column on the left, right? So the index for the index here just gave you the idea which bit we're going to add here. So first value going to be, the bit in the index 32, which is 0. That's index 4. Index 4, it's 0. Index 8 is 0. Index 12, 0. Index 16, index 20, index 24, and index 28. These are all 0. So we basically added 2 columns, right? That makes the matrix becomes 8 by 6, which contains total of 64 of 50 58 of 48 bits. Sorry. Okay. So that's the 48 bit after the expansion and the permutation. So we complete the expansion permutation here. So now we're here. We have this 48 bits. Okay. So the next one we're going to do is we're going to perform the exclusive OR operation with the key K1 we call the subkey. Okay. The subkey we'll be talking about later. But the subkey is also 48 bits. Okay, so now we have 48 bits and 48 bits, and then we're going to perform the operation called the exclusive OR. And remember, the exclusive OR operation basically defines like this. So if we have a number 0, then after the exclusive OR, it becomes the 0. If it's 0, 0, after exclusive OR, it's 0. 0 exclusive OR 1 is 1. 0, oh, I'm sorry, 1 exclusive OR 0 is 1. and the 1 exclusive OR 1 is 0. So that's a definition. And in most of the time, we actually use the plus with a circle to represent the exclusive OR. So we use X OR, but it actually means exclusive OR operation. Okay. Okay, so we have completed the expansion and the permutation operation. So we actually create a 48-bit string. Now that 48-bit string gonna actually perform the exclusive OR operation with the 48-bit subkey K1. Okay. Now how are we gonna perform this? So that's the 48-bit string after expansion permutation. If you look at this, you can see that we actually reorganize these 48 bits again. Remember, after we actually complete the expansion and the permutation, we actually generate a matrix of 8 by 6. Okay, so which is 48. And then we can reorganize this into 6 by 8. So we just reorganize into a matrix of 6 by 8. However, so we actually rename the index. The first one is the index 1. The end of the first row is index 8 because it's a column 8. Okay, so it's still actually 48-bit, but we actually, again, we reorganize these matrix. Now, the other side is the 48-bit subkey called K1. Okay, it's originally generated from the 56-bit key, and then use the permitted choice. Eventually, we get the 48-bit subkey. Now, at this moment, don't ask me how we get this number. We will talk about this later, okay? Because we already know what was the key, right? The key was 64-bit. It's all 0, all 1, all 0. But then we immediately, convert the 64-bit key into a 56-bit key. Okay, and then we're going to pass through a couple of left shift, and then after permitted choice 2, then we eventually get to the subkey K1. So now we have a 48-bit string and a 48-bit subkey. Then we're going to perform the exclusive OR operation. Now, exclusive OR operation going to perform, bit by bit. Okay, the first bit gonna actually, do the exclusive OR with the first bit on the key. So that means 0, exclusive OR 1. What's the result? 0, 1. So based on the definition, okay, that's 1, right? 0, 0, that's 0. 0, 0, it's a 0. 0, 1, it's 1. 0, 0, it's a 0. And next one is also 0, 0, and the 0, 1 is 1. Okay. So we can actually, similarly, we can do the second row, and with the second row here, it's a 0, 1, 0, 1, 0, 0, 1, 1. Okay. And then this one, third row here, it's a 1, 1, 1, 0, 0, 1, 0, 1. Okay. And then the next row, it's a 0, 1, 0, 0, 0, 0, 1, 1. And then the fifth row here and the fifth row here. So you're going to do this, pairwise. 0, 0, it's 0, 0, 0, 0, 0, 0, 0, 1, 1, it's also 0, right? And 0, 1, it's 1. And 1, 0, 1, 1, 0, 1, 0, 1, 1. And we can actually fill the last row. 0, 1, it's 1. 1, 0, it's also 1. And 0, 1, it's 1. 1, 1, it's 0. 1, 1, it's 0. And 0, 1, it's 1. 0, 0, it's 0. 0, 1, it's 1. So basically, that's the output after the exclusive OR operation between the 48-bit string and the 48-bit subkey. Okay, so now after the exclusive OR operation, we get another 48-bit output. So that's the 48-bit output. So we're now here. Okay, so the next process is going to be the substitution / choice. It's called the S box. Okay. So that's the final result for the exclusive OR operation, as we have done in the previous slide. Okay, so we're here now. Okay, the next one, we have a 64-bit. And the next one, we're gonna go through the, substitution / choice. It's called S box. And we're gonna shrink the 48 bits to 32 bits. How are we gonna do this? Let's see. Okay, so after the exclusive OR operation, we have the output, which is 48 bits. So the next step is going to be the S box, we just discussed earlier. Now, before we do that, we need to reorganize these 48 bits again. Now, at this moment, the 48 bits is organized into 6 by 8. Okay, so now we need to actually partition it into a block of 6 bits. Okay, so that's the first block, 100, 100. Okay, we have this one here. And then the second block, okay, 01, 01, 01. Third block, so we pick the 3 in the row 2 and the 2 in row 3. And the fourth block, okay, so we continue to partition. Okay, and the last block. So we have a total of 8 blocks of 6 bits. 8 blocks of 6 bits. Okay. Now we're gonna actually go over the S box. Now S box consists of 8 tables. Okay. So that's a table C.2. Okay. Now you have the first table S1, S2, and all the way to S8. Okay. The table is actually 4 by 16. Okay. So the first row of the table is, we call it row 0, and row 1, and row 2, and row 3. And the first column is column number 0, column number 1, column number 2. Since we have a total of 16 columns, so the last column is column number 15, right? Because we start from 0. Okay, same thing for S2 and S3. Now, look at this very carefully. How we gonna, use SBox? SBox is basically a simple table lookup, but before we do, we need to first identify the row number and then the column number. Okay. So what we're gonna do is we're gonna actually pick the first bit and the last bit. Okay, and then we create a new number. It's 1 0. So 1 0. That becomes the raw number. And the middle one, in this case, it's a 0 0 1 0. That becomes the column number. Okay. So same thing with the second 6 bits. The first one bit combined with the last bit, it's a 0 1. And then we pick the middle one, it's a 1 0 1 0. And the same thing with the remaining six bits, 0 1, and then 0 1 1 1, 1 1, 0 0 1 0, 0 0 1 0 0 0, 1 0, and 1 0 0 0, 1 1 1 1 1 1, and 1 1 0 0 1 0. And the next thing we need to do is we need to convert each of the binary number here into decimal. Okay. What is the decimal value for binary number 10? Okay. Let's briefly list some of the, numbers here. 0 0 is corresponding to decimal 0. 0 1 is 1. 1 0 represent 2. And 1 1 is 3. Okay. If we continue, okay, so then 1 0 0, that's 4. And the 1 0 1, that's 5. So that's a relationship between the binary number and the decimal number. Now for 4 bits, okay, so this one, let's first look at the raw number, because raw number contains only 2 bits. So 1 0 is actually 2. 0 1 is actually 1. 1. 1 1 is actually 3, right? 0, 2, 3, 3. Now the second one, for 4 bits, this is 0 0 1 0, it's corresponding to 2. Now 1 0 1 0, what is this, the value for 1 0 1 0? You will find out 1 0 1 0 is actually 10. Because eventually you're going to find out 1 0 0 0, that's corresponding to the decimal 8. Okay. And this 1 0 is 2. So 1 0 1 0 is 8 plus 2. It's a 10. 0 1 1 1. So 1 1 1 is actually 7. And 0 0 1 0, that's 2. 1 0 0 0, that's 8. 8. Now, what about all 1 for 4 bits? That's going to be interesting. For all 1, that's 15. Okay. So we're going to talk about this, if you, don't understand these conversions between binary and the decimal. And the 0 0 1 0, that's 2. So that's the raw number, column number. Okay. So now we're going to find out the corresponding value, which number this is going to actually map to. So called, the the row number 2, column number 2. So that's row number 1, row number 2. Oh, I'm sorry. It's row number 0, row number 1. So row number 2 here, column number 2 is a column number 1, column number 0, column number 0, column number 1, column number 2. So it's row number 2, column number 2, that's corresponding to number 14. Row number 1, column number 10. Row number 1, so that's row number 0. Row number 1 is this. Now the column number 10, it's a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 1. Now, so the third one, we're going to look at the S3. Okay, it's a 1, 7. So 1, where's 7? 0, 1, 2, 3, 4, 5, 6, 7. So that's this. Okay. And the 3, 2. 0, 1, 2, 3. So row number 3, column number 2, 0, 1, 2. So that's 0. 0, 8. So that's the next S table. 0, 8, 0, 1, 2, 3, 4, 5, 6, 7, 8. So that's 8. And 2, 8, 0, 1, 2, 8, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's a 2, 8, it's a 7. And a 3, 15, 1, 2, 0, 1, 2, 3, 15 is the last one. Okay, so that's 13. And a 3, 2. Oh, sorry, that's not 13 because we're looking at the S7, right? So S7 is 12. And 3, 2, we look at the S8. So each corresponding to a table on the right. Okay, so the last one, 3, 2. So we have 1. Oh, that's 3, 15. That's 3, 2, 3, 2, 3, 0, 1, 2. So that's 14. And then we could convert each of the number back to the binary. So we initially have 6 bits. Now each 6 bits is going to convert into 4 bits. Okay. So what's 14? How can I write 14 in 4 bits? Okay. 14 is 1110. Okay. Or 1 is 15. Okay. Now what about 1? 0001. 10. 10 is 1010. And 0, it's 10000. 8, it's 1000. 7, 0111. 12, what is 12? So it's a 1100. 14, it's 1110. Okay, so now you got these binary number, each has 4 bits. Okay. So now you can see each 6 bits going to convert into 4 bits with the S table. So that's total of 32. Okay, so here's a summary of the output after the S box. Okay, so from 48 bits down to 32 bits. Okay, so using the S box, we convert 48 bits down to 32 bits. So we initially have 48 bits. Now we are here, 32 bits. So the next process is the permutation function here, which is defined in table C.1d. Now here's the C.1d, okay? So in order to use the C.1d again, these are the index. Okay, so we reorganize the 32 bits into 4 by 8. Okay, because that permutation function is 4 by 8. So this is the index. Okay, these are the index. Now, so following the permutation function, so we're going to see, the first element after permutation, function is 16, the index 16. Where's the index 16? So that's 16. Okay, 7, that's 7. 20, where's 20? 17, 18, 19, 20. Again, 0. 21, 0. And 29, 25, 26, 27, 28, 29, that's 1. 12, so 9, 10, 11, 12, it's 0. 28, 25, 26, 27, 28, and 17. So we have 17 here, it's 1. And we can actually, similarly, we can fill the rest of the bits based on the permutation function, based on the index defined in the permutation function. Okay, so we're going to skip that for now. Okay, so now this is the final output after the permutation function. So now we are here. We got the 32-bit output. Okay, after the permutation function. And then that 32 bits will perform the exclusive OR with the L0. Okay, which is the 32-bit on the left side after the initial permutation. Now this is R0. Okay, so now we're going to perform the exclusive OR with L0. Now, so this is L0. Okay, so now we're going to perform the exclusive OR between the result after permutation function and the L0 here. So now again, with exclusive OR operation, which is defined as, if we have a 0 and then we have an exclusive OR with 0, now we got a 0. 0 exclusive OR with 1, we got a 1. And a 1 exclusive OR with 0, we got a 1. And a 1 exclusive OR with 1, we got 0. So that's the definition for the exclusive OR. So let's do this bit by bit. So the first bit, the bit with index 0 or index 1, with the first bit here. So it's a 0 exclusive OR with 0. So we got a 0. 0 exclusive OR 0, we got 0. So we continue with the exclusive OR operation. We'll find out the first row going to be 0, 0, 0, 1, 0, 0, 1. Okay, and now we look at the second line, the second row. So after the exclusive OR, the result is going to be 1, 0, 1, 1, 0, 0, 1, 0. Okay, then let's look at the third row. So 1, 1, we got a 0. 1, 1, we got a 0. 1, 1, we got a 0. And a 0, 1, we got a 1. Okay, and then we got 0, 0, 1, 1. Okay, so now the last row Okay, so it's a 0, 1, we got a 1, 0, 0, we got a 0, 1, 1, we got a 0. Okay, 1, 1, we got a 0. And 0, 0, we got a 0. Okay, so it's a 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1. Okay, so that's the final result. Okay, that's a 32 bits. That's a 32-bit output after the exclusive OR operation. So that's the R1. Okay, so we got R1 here. Now, so this is the output, of the round 1. Okay, the first round. Now, what is the left side of the output? The L1. It's very straightforward because if you look at this diagram, so L1 is actually R0. Okay, so L1 is R0. So now we got L1 and R1, which is the output after round 1. Okay, so that's the final result. Okay, that's R1. And also, as we know, the L1 is actually the R0. Okay. Okay. Okay, so let's summarize this final result after first round. So now we complete the calculation of R0, and then in the final result, L1 is directly copied from R0. So this is actually the final result after the first round. Okay. Now let's actually check out the other side. That's the operation on the key side. Okay. Okay, so let's look at the right side of the DES. That's the key generation. Okay. So the table C.3 on the right basically defines the following operations. The first table A, this is actually the table that basically reduced the 6-bit import key to 56 bits. Okay, this is done by eliminate the 8th column. Okay, so once we have a key and we organize the key as 8 by 8 matrix. Remember, that's initially that's a 64-bit. So once we organize the key into 8 by 8 matrix, so that here this is again the index for each of the bits, okay, for the key. And then we eliminate the last column. So this is actually the 56-bit key we're going to use throughout the whole DES processes. And the second one, we define the permuted choice 1, and we also call the PC1, PC-1, permutes the 56-bit key based on the rule defined in the table. Okay, and then we have a permuted choice 2, basically permutes the 48-bit based on the rule defined also in the table on the right. Okay, so this is permuted choice 1, this is permuted choice 2, and then we're going to schedule the left shift, which is also defined in each round of the DES operation. Okay, now depend on the round number, we can actually do the left shift, either one position or two position. So round one, we do the left shift one position, and round two, also one position. Round three, we're going to left shift it to two positions. Okay. So let's take a look. Okay, so let's look at the right side of DS, which is the key generation. Okay. As we mentioned earlier, the input key is 64-bit. Okay, here's the 64-bit key, which is actually, 8x8 matrix. Now, let's take a look at the table C.3a. So we first going to eliminate the last column. Okay, so that's this one. So 64-bit key, we eliminate 8 bits. So there's only 56 remaining. Okay, so now we're going to actually reorganize the remaining bits based on the C.3b, the permitted choice 1. Okay, so based on this permitted choice 1, we know that the first bit will be the bit in index 57. Okay, so that's this one. Now the second one is 49, so that's this one. And if you look at the first row, we'll find out 56, 49, 41, 33, 25, 17, 9. That's this one. Okay, so from the bottom, slowly goes up. Okay, so the first row is going to be 1, 0, 1, 0, 1, 0, 1. Okay, it's a first row, but from bottom up. And then the second row, the first one is the index 1, which is this. Okay, and then 58. Where's 58? So 57 is this, 58 is this. So we have a 1, 1, 58, and then we have a 50. We have 42. So it looks like the second one going to be, the second row going to be the first one is index 1, it's a 0. And then we switch to the second row, a second column, I'm sorry, and from bottom up. So it's a 1, 0, 1, 0, 1, 0. Okay, so it's a 0, that's index 1, and then 1, 0, 1, 0, 1, 0. Now, for the third row, okay, of the output, we start from here, goes up, and then goes back to the row, column number 3, bottom up. Okay, we're going to pick 1, 2, 1, 2, 3, 4, 5, 6, 7. So that's it. So it's a 1, 0, 1, 0, 1, 0, 1. And then the fourth row going to be 19. So that's 19. And then 11. And then 3. So we're going to start from 19, from bottom up. And then we switch to column number 4 and the bottom up. Stop here. Okay, it's a 1, 0, 1 0 1 0 1. So that's the first half. The second half is the first one, the index 63, okay, and then 55. Where's 63? So the last column, that's 64, right? 63 is this one, okay. Now where's 55? That's 56. So 55 is this one, okay. 47 is this one. That's 40. Okay, this is 40, and this is actually that's 47 or 48. Okay, 39 is this one because this is 40. Okay, so we basically, for the fifth row, we start from 63 and then 55 and then 47, 39, 31, 23, and 15. So start from the last row, actually from row 7, because last row has been eliminated from row 7 from bottom up. So it's 1 0 1 0 1 0 1. Okay, and then the next row, it's a 7 62. That's 7 62 54 46 38 30 22. So you start from this one and then include this 6 bits. So it's 0 1 0 1 0 1 0. Remember, it's always going from bottom up. Okay, and the next one gonna be here, goes up, and then goes up. We stop here. So it's a 1 0 1 0 1 0 1 1 0 1 0 1 0 1. Okay, what's the last one? So we start from here, 0 1 0. So it's 0 1 0, and then because that one has been counted, okay, so we're gonna actually, the remaining one is 0 1 0 1 0 1 0. Okay, so 0 1 0 1 0 1 0. Okay, so we just reconstructed the matrix using the permitted choice 1. So we got this. Okay. Okay, here's a summary. We eliminate this, okay, the last one, and then we reorganize the remaining 56 based on these permitted choice 1 table, and so we generate this new 56 output. And then the first half is called C0, and the second half is called D0. Okay, so let's move forward. Okay, so after the permitted choice 1, we eventually get the result C0 and D0. Okay, now C0 is 28-bit, which is the first half of 56 bits. And the D0 is also 28 bits, which is the second part of the 56 bits. So now the next thing we're going to do is do the left shift. Okay, so here we have C0, and here's a D0. Now the left shift we're going to perform on both C0 and the D0. How many shift we're going to perform. Since we are working on the round number 1, the first round, so we can actually do the bit rotation once. So that means we're going to shift it to the left, circularly. So here's what we can do. Okay, so now the second bit will override the first one, and then the third one is going to override this one. This will override this. This will override this. This bit will override this, and this one override this, and then this 0 going to override this. So we're going to do the shifting. So this is a 0, 1, 0, 1, 0, 1, 0. Okay, so that one will be actually moved all the way after the last one. So this 0 becomes the first bit. This one becomes second bit. This one becomes third bit. Now initially the first bit will shift all the way to the bottom. Okay, so we're actually going to do this shift. So now we have a 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, and that one was initially the first bit. Okay, so we're going to do the left shift. Everything shifted to the left. So because the first one, there's no left because it's already the first one. So we're going to shift this to the bottom of it. Okay, move the one here. And then we're going to shift, each one going to be shifted to the left. Okay, so now we have 0, 1, 0, 1, 0, 1, and that 0 is coming from here. Okay, and then this one going to move here, move here, move here, move here, move here, move here, and that one going to actually shift it here. Okay, that 0 going to shift to the end. Okay, so we have 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, and a 1, 0, 1, 0, 1, 0, 1. That's the initially was this first one. So after the left shift for both C0 and D0, we got this result. Okay. Okay, so that's the final result after the left shift. Okay, so we have this one here, 28 bits and 28 bits after the left shift for C0 and D0. Okay, so this is right here. So now we end up with the 56 bits, right? We combine these two blocks and which create the 56-bit binary string. Okay, so after we perform the left shift from C0 and the D0, so we got this 28-bit string and another 28-bit string. So the top one is left shifted from C0 and the bottom one is left shifted from D0. So now we put the index on each of the bit before we perform the permitted choice 2. So now let's take a look at the permitted choice 2, which is the table C.3c. And so the first index is 14. So that means we're going to place the first bit here, which is index 14. and the second one is index 17. So now this is a 17. So we put 0 here. And then index 11. So that's so we have 8, 9, 10, 11. So that's the bit with index 11. So and then 24, it's 1. And then the index 1, which is 0. And the index 5, which is 1, 2, 3, 4, 5, 0. And index 3, which is 0. And index 28, which is 1. Okay. So then we're going to build the second row based on the permuted choice 2. So we build a second row and a third row. So then we're going to complete the whole permuted choice, and then we got a 48-bit output. Okay, so here's the final result, which is 48-bit K1. That's a subkey. This subkey will be used in the round 1 on the plain text side. Okay, now here's the brief summary. So on the top left, this is the plain text, which is 64 bits. And on the top right, that's 64-bit key. Okay. Now, after the initial permutation, the 64 plain text becomes 64-bit output. And left side is called L0, and the right side is called R0, which is the input for the round 1, the first round. Now, after the first round, we generate the 64-bit output. Okay. The left side is L1, the right side is R1. Now, L1 and R1 becomes the input for round 2. So the output is going to be L2, R2. And then it becomes the input for round 3. The output is going to be L3 and R3. So we have a total of 16 rounds. Okay. That's the plain text side. Now, for the key generation, the initial 64-bit key becomes 56 bits after the permitted choice 1 by eliminating 8 bits. Now, we divide the 56-bit into 2 parts. The left part is C0 and the right part is D0. And we perform the left shift for C0 and the left shift for D0. And then we combine these results into a 56, and then we perform the permitted choice 2, which eventually generate a 48 bits. Now that's the subkey, which is key 1, which can be used on the plain side for round 1. Now, after the left shift, so this also create the left side C1, and then the left after left shift of D0, it becomes right side D1. Okay, now C1 and D1 will be used to generate the subkey K2. Okay, so then each time before you generate the K and subkey, we're gonna do the left shift. Okay, so sometimes the left shift is gonna be 1 position, sometimes the left shift is gonna be 2 positions. Now, which is defined by one of a table C.3D. Okay, so that's basically the summary of the plain text. So after round 1, we eventually get L1 and R1.